Welcome to the MOOCs course Advanced Thermodynamics. The title of this lecture is Excess Functions and Activity Coefficients. Before going into the details of this particular lecture, we will be having a kind of recapitulation of what we have derived in our previous lecture. In the previous lecture, we have derived a relation between excess Gibbs energy and activity coefficient. So, that we start with that part and then we go into the more details of obtaining the activity coefficient from this excess Gibbs energy, that is what we are going to see. So, we have defined excess thermodynamic property as difference between the thermodynamic property under real conditions minus thermodynamic property under ideal conditions, or what is the thermodynamic property that is in excess of ideal condition, that is what we have defined as a excess thermodynamic property. And then let us say if you want partial molar Gibbs energy, excess partial molar Gibbs energy, then that should be Gi bar minus Gi bar ideal, and then we have seen Gi bar real is nothing but RT ln Fi real, and then Gi bar ideal is nothing but RT ln Fi ideal. So, that you substitute here and then simplify, then you have Gi bar is nothing but RT ln Fi real by Fi ideal. So, Fi ideal, if you substitute Ri xi, then we get Gi bar is equals to RT ln Fi by Ri xi. Okay. We know that the ideal solution is one for which activity is equal to the mole fraction, that is, this is what we have seen for the case of ideal solutions. Okay. For the case of ideal solutions, so this is what we have seen, and then for the case of non-ideal solution, whatever the activity coefficient is there, that we have defined it as gamma is equals to A by xi. So, both are interrelated, because if you have gamma is equals to 1, that is for the ideal condition, then Ai is equals to xi. Okay. Then if you set standard reference state fugacity Fi naught as Ri, then what you will be having? You will be having this Fi by Fi naught is nothing but Fi by Ri here in this case. Okay. And then this Fi by Fi naught definition is nothing but activity. Fi by Fi naught we have seen as a kind of activity. So, A is equals to Fi by Fi naught, right. Now, so that we can write Fi naught if you are writing Ri. So, then A is equals to Fi by Ri, and then A is equals to gamma I xi also we have written. So, what we can write in place of Fi by Ri, we can write Ai, and then Ai in addition it is also equals to gamma I xi. So, in this equation in place of Fi by Ri, if you write gamma I xi, then you have RT ln gamma I xi by xi. So, then that you have RT ln gamma I. So, that is the relation. This is the important relation that we have derived in the previous lecture, and then this relation we are going to use extensively as long as we are discussing non-ideality in the case of liquid solutions. So, now other simple approach is that Gi bar we have seen this RT ln Fi real by Fi ideal. So, Fi real we know that it is nothing but xi gamma I Fi naught, and then Fi ideal is nothing but xi Fi naught simply. So, this xi Fi naught if you cancel out, then also you are having Gi bar is equals to RT ln gamma I, right. So, the other way, let us say this is if you have this one is as a kind of partial molar excess Gibbs energy, then you can write this Ge, that is excess molar Gibbs energy, you can write it as RT sigma xi ln gamma I, because we know this for excess functions also this property holds good in, right, that is what we have seen in previous lecture. So, this Me is nothing but whatever the number of moles Nt small me, right, sigma Ni Mi bar E. That means if you write this small m e, then it should be sigma n I by n t is x I m I bar e. This is what you are going to have, and then in this case m I bar is nothing but whatever g I bar e. So, g I bar e is nothing but r t ln gamma I. So, that should be sigma x I r t ln gamma I. So, if you take r t common, you can write r t sigma x I ln gamma I as nothing but g e. That means, if you have information about g e, then you can find out the activity coefficient of individual components, you can find out the activity coefficient. Once you know the activity coefficients of individual components, then you can also know the molar excess Gibbs energy as well. Either way, this equation can be used. If left hand side is known, right hand side you can find out. If the right hand side is known, left hand side you can find out without any difficulty. This is what we have seen. We have also seen relation between molar and partial molar excess Gibbs energy. So, this G E is equals to R T sigma x I ln gamma I we have seen, and then as I mentioned, this G E small g e is nothing but molar excess Gibbs energy. If you multiply this one with N T, it will give the total excess Gibbs energy, and then right hand side whatever the x I is there, that we are writing N I by N T. So, that only if you bring into the left hand side. So, then we have N T G E is equals to R T sigma N I ln gamma I. This is what we have. Now, if you wanted to know G I bar E, what you have to do? You have to partially differentiate this N T G E with respect to x I. Then you will get G I bar E is equals to dou by dou N I of N T G E, and then so this part if you partially differentiate with respect to Ni. So, R T is common, and let us say when ln I constant, then dou by dou Ni of sigma Ni is nothing but 1. So, ln gamma I plus here in this case Ni is constant, and then dou ln gamma I by dou Ni you are having. So, such kind of components you will be having n number of components depending on the number of components. Let us say if you have if you do all this summation of all those differential terms, then you have sigma k n k dou by dou n I ln gamma k at T p n j as constant. But this term we know from the Gibbs-Duhem equation, this summation is going to be 0. This summation is going to be 0. Then under such condition also what we have? We can have G I bar is equals to R T ln gamma I. So, knowing the importance of how much important is this equation. So, we are trying to obtain different forms of this equation, or trying to get the same equation by different approaches. So, now in this lecture what we will be using? We will be using some kind of expression for G E or G bar E, whichever is available, and then trying to find out this gamma I. And then from there we try to establish more on the this activity coefficient. So, if this gamma I is equals to 1, then we should call it as a kind of ideal solution, right. So, and then that is possible when this G is equals to 0, right. If it is ideal solution, then all the interactions are uniform, same, then obviously there will not be any kind of excess property, and then that should be giving that excess property as a 0. So, now we try to obtain activity coefficients from excess functions in binary mixtures. We start with the binary mixture for simplicity, and then we can extend to the multi-component mixtures. Consider a binary mixture where excess properties are taken with reference to an ideal solution where standard state for each component is pure liquid at constant temperature and pressure of the mixture. So, that means if the reference state is such a way that the for each component the reference state is a pure liquid. So, that means x I tends to 1, that is the case has been taken as a kind of reference state. So, that means we are doing this calculation with reference to Lewis-Randall rule which says the reference state is a kind of the Figasti under the reference state is nothing but the pure component Figasti. If the component is pure, so then corresponding Figasti is pure component Figasti, that should be taken as a kind of Figasti coefficient or Figasti for the reference state. In such case, any expression for molar Gibbs energy must obey two boundary condition. If this has to be followed, then it must obey two boundary conditions. What are the two boundary conditions? So, that is if it is a binary mixture, then two boundary conditions it should be obeying. So, why? Because in the binary mixture we have x1 and then x2. Let us say x1 tends to 1, then what does it mean by component 1 is a pure component, isn't it? So, that means second component is not there. So, in that should be giving GE is equals to 0. Other extreme is that x2 tends to 1, that means the mixture is not existing, it is pure second component is existing. If the component is pure, so then obviously that solution is a kind of ideal solution. So, ideal solution, the excess properties are 0. So, for that condition also GE should be 0. So, these two boundary conditions should be obeyed if you are taking this as a kind of reference state. What is this reference state? That at the temperature and pressure of the mixture, standard state for each component is pure liquid state. Okay. So, that is GE should be 0 when x1 is equals to 0 and GE should be 0 when x2 is equals to 0. These two boundary conditions should be satisfied for the case of a binary mixture. So, that means indirectly you should have a kind of a GE as a kind of function of x1 and x2 such a way that this function should obey these two boundary conditions. Alright. So, the simplest one is that this x1 and x2 are being multiplied in that function in each term, right, with some powers or something like that. So, then it is possible that these two boundary condition would be satisfied. So, but we start with a kind of simplest one that GE is equals to A x1 x2. GE is equals to A x1 x2, A is a constant, temperature dependent constant, but independent of the composition. So, now if x1 is 0, then GE is 0, if x2 is 0, then also GE is 0. So, this is the simplest possible expression for GE, okay, satisfying these two boundary condition, and this is for the binary mixture, Okay. So, this is also known as the 2 suffix Morgell's equation. So, for this case, if that is the molar excess Gibbs energy is defined using this equation. So, then what are the activity coefficient of those two components 1 and 2 in the liquid mixture at the given temperature or pressure as a function of mole fraction. So, that is what we are going to see now. Now, as mentioned, this is a constant, temperature dependent, but composition independent constant. Now, if this A should have the unit same as GE. So, that is the energy units it must have. It is the characteristics of components 1 and 2 that depends on temperature, but not on the composition. It is independent of pressure as long as the pressure is low to moderate. As long as pressure is low to moderate, then also it is independent of the pressure. Now, for this case, if you wanted to find out gamma 1, gamma 2, so then GI bar E is equals to RT ln gamma I, this is what we have already seen, we have derived. So, now that means if you wanted to get ln gamma 1, you have to do ln gamma 1 is equals to 1 by RT dou by dou N1 of NT GE at constant temperature, pressure, and 2 you have to do at constant temperature, pressure, and 2 you have to do because it is a binary mixture. So, that differentiation you have to do with respect to N1, whatever the GE is given, that you multiply by NT and then differentiate with respect to N1 and then divide by RT. So, then you will get ln gamma 1. Here Ni is nothing but the number of moles of component I, Nt is the total number of moles of that particular mixture, and then x1 is nothing but N1 by Nt and x2 is nothing but N2 by Nt. Then now this equation number 3 we are going to solve for gamma 1 and gamma 2. So, let us say gamma 1, if you do, gamma 1 is equals to 1 by RT dou by dou N1 Nt Ge at constant Tp N2. So, now here what we do, Ge is nothing but A x1 x2, that is given for 2 suffix Morgul equation. Ge is A x1 x2. So, A is a constant that you can take out, and then N1 by Nt is nothing but x1, N2 by Nt is nothing but x2. So, this Nt is cancelled out, and then this N2 is also independent of N1. So, that also you can take out as a constant outside of the differentiation. Then you have ln gamma 1 is equals to A N2 by RT dou by dou N1 of N1 by N1 plus N2. Now, if you differentiate this one, you will get here N2 by N1 plus N2 whole square, and then N2 is multiplied here. So, N2 square by Nt square is there. So, A N2 square by RT Nt square is there. So, that we can write ln gamma 1 is equals to A x2 square by RT. So, now here we can see this gamma 1 is written as a function of x2, not as x1. Why? Because this gamma 1 is there, because with this component 1, the component 2 is coming and mixing and then forming some kind of real solution. Non-ideality is there because of that second component. So, that is the reason in general these activity coefficients are represented as a kind of other component, as function of mole fraction of the other component. Let us say here for a binary mixture, if you are writing gamma 1, it is written as a function of x2, because gamma 1 is there existing because of this second component is coming and joining with the first component, right. So, that is the reason. Rather the same equation can be written as a kind of A into 1 minus x1 whole square by RT, but still despite of that one we write this form A x2 square divided by RT, right. Same gamma 2 also, if you do derivation you will get ln gamma 2 is equals to A x1 square by RT. So, now here gamma 2 we are writing as function of x1, because gamma 2 whatever the second component, in the second component non-ideality is there because of whatever the first component is coming and then joining with the second component to form the mixture. Okay. So, that is the reason gamma 2 is written as function of x1. So, this is the common tradition that may be followed, and then you often see such kind of expression rather than gamma 2 writing a function of 1 minus x1 whole square and all those kind of things. Okay. So, these ln gamma 1, gamma 2, ln gamma 1, ln gamma 2 are for 2 suffix Morgul's equation. Okay. So, this is how you can develop the activity coefficient of components that are present in the mixture using the GE expression. Okay. So, binary mixture, if that is binary mixture, excess molar Gibbs energy of that mixture is represented by 2 suffix Morgul's equation. Their corresponding non-ideality whatever is there in the solution represented by gamma 1, gamma 2, they have been obtained as a kind of exponential of A x2 square by RT and exponential of A x1 square by RT respectively, right. So, now how much are reliable these equations, that also one has to check, and an obvious way is to check with the experimental results that are available. Okay. It has been found that equations 4 and 5, that is 4 is nothing but ln gamma 1 is equals to A x2 square by RT, and then this one is ln gamma 2 is equals to A x1 square by RT is nothing but the ln for the second the equation number 5. Right. These are the equation number 4 and 5. They provide a good approximation for many simple liquid mixture, that is for mixture of molecules that are similar in size, shape and chemical nature. These two equations are symmetric in the sense when you plot ln gamma 1 versus x1 and then you also plot ln gamma 2 versus x2, then you can see whatever the curve that is being formed, they are mirror images of each other. In fact, you can see from these equations also ln gamma 1, ln gamma 2. So, the x1 is replaced by x2 in the other case, ln gamma 1 a x2 square by RT. So, now x2 is replaced by x1, then you get ln gamma 2. So, that means they are mirror images of each other, and then if you have this ln gamma 1 versus mole fraction either x1 or x2 mirror images of each other, then we call those activity coefficients or symmetric activity coefficients. We see pictorially also some cases, no. So, at infinite dilution, the activity coefficients of both components are equal to, let us say if it is infinite dilution, right. So, that is component gamma 1 infinity stands for the activity coefficient of the solution where component 1 is present in very small quantity and then component 2 is present in large quantity, that component 2 is almost kind of having mole fraction close to 1. So, that means we can write ln gamma 1 infinity is equals to A by RT, and this is almost close to 1. And then similarly in the second case ln gamma 2 infinity, because now in the second case the second component is under the infinite dilution condition, that is it is present in very small quantities in the mixture, and then component 1 is present in such a large quantity that compared to the component 2, the mole fraction of component 1 is almost close to 1. So, that is A by RT is equals to, that is A by RT multiplied by x1 square, here in this case x1 is 1. So, that means for these two suffix Morgul equations, at infinite dilution conditions, the activity coefficients of both components are same, that is exponential of A by RT. That is gamma 1 infinity is exponential of A by RT, and then gamma 2 infinity is exponential of A by RT, either way. Fine. So, coefficient A may be positive or negative depending on this, because GE we are writing as A x1 x2, and then GE is nothing but G under real conditions minus G under ideal conditions, right. Depending on the magnitudes of G real and G ideal, this G can be positive or negative, and accordingly the constant A may be positive or negative, and it is general function of temperature obviously. And then however, for simple system over a small range of T, A is nearly constant. For example, if you take argon oxygen system, if the temperature range is limited between this small 83 to or 84 to 90 Kelvin roughly, then A is roughly decreasing from 148 to 141 joule per mole. So, such small decrease is there for the case of simple system, for the case of simple systems like argon and oxygen. But if you have some non-polar solutions, under such conditions A frequently falls with increasing temperature. Let us say for example, if you take benzene and cyclohexane example, right. So, benzene and cyclohexane, again if you represent by 2 suffix Morgul equation, whatever the excess Gibbs energy or the molar excess Gibbs energy of benzene and cyclohexane system, liquid system, if you obtain their excess Gibbs energy or molar excess Gibbs energy, and then if you mathematically represent it by 2 suffix Morgul equation having GE is equals to A x1 x2 form, then that A constant is going to decrease with temperature, as the temperature increasing from 303 Kelvin to 320 Kelvin, A is decreasing from 1268 to 1114 joule per mole, right. So, this is how one can make analysis of activity coefficients from G information, obtaining this activity coefficient from G information, and then further analysis one can be making further analysis of those component. So, now this is the simplest one as we said. So, obviously, it is not going to be reliable or suitable for all components. So, then we have to make a kind of correction or adding more terms kind of thing. And then one of the convenient form is that writing this one in a series expansion form like this. So, that is GE is equals to x1 x2 multiplied by a plus b x1 minus x2 plus c x1 minus x2 whole square plus d x1 minus x2 whole cube and so on. So, now here we can see binary mixture again. So, when x1 tends to 1, that means pure component 1. So, x2 is 0. So, then GE is going to be 0. When x2 is equals to 1, then x1 is going to be 0. So, then again also and under such condition also GE is going to be 0 irrespective of the values of this a, b, c, d, these parameters constant. So, for this binary mixture, this expression as well follows or they obeys both the boundary condition, that is when xi tends to 1, GE is tending to 0, right. And now within this parenthesis whatever there. So, if you have only the term a, only first term a, up to that term only if you include, then it is called as a 2 suffix Morgul equation, that is simply a x1 x2, you are not including additional term. If you include one more term, that is x1 x2 multiplied by a plus b x1 minus x2 up to this one, then the same equation is known as the 3 suffix Morgul equation. The same equation is known as the 3 suffix Morgul equation. So, if you add one more term, that is plus c x1 minus x2 whole square, then this equation is known as the 4 suffix Morgul equation, right. And then we have seen when it is 2 suffix Morgul equation. So, this ln gamma 1 is simply a x2 square by RT, and then ln gamma 2 is simply a x1 square by RT, and then mathematically also they are clear, and then we can realize this ln gamma 1, ln gamma 2 are symmetric coefficient or symmetric activity coefficients, right. But when you added this second term b x1 minus x2, then what happens, that the equation becomes 3 suffix Morgul equation. So, this is not going to be valid, they are going to have additional terms or altogether different functions it may be having, right. So, then because of that one additional terms, what happens, whatever the activity coefficient that you get for the third and fourth or higher suffix Morgul equation, they are not going to be symmetric, they are not going to be symmetric, okay. So, that we can check anyway, we can cross check, we can simplify this equation and then get the gamma 1 gamma 2 for 2 suffix 3 suffix 4 suffix Morgul's equation, and then you can check gamma 1 gamma 2 by 3 different forms. So, you can get only the 2 suffix Morgul's equation is giving a kind of symmetric activity coefficient, but third and fourth Morgul's equation or 4 suffix Morgul equation, they are not giving a symmetric activity coefficients. So, if you generalize this one, you can write generalized one like GE is equals to x1 x2 sigma aj x1 minus x2 power j. So, now what we do, we take this equation and then try to obtain what are the ln gamma 1 and then ln gamma 2 forms, okay. So, here again A, B, C, D are the temperature dependent constant, but independent of the composition, and they have to be determined experimentally obviously. That is, let us say A, how did you find out that gamma 1 infinity is exponential of A by RT. So, you can have a kind of solution with one component 1 is in a very small quantity, so that you can say that infinite dilution conditions are there. Then you can find out the activity coefficient for solution, that solution experimentally, and then curve fit that data using this expression gamma 1 infinity is equals to exponential of A by RT, and then you can find out what is A for different temperatures. That is simply by curve fitting, or let us say under any condition, if you plot ln gamma 1 versus composition x. So, you may be having different curves like this. So, different curves, you can have different temperatures, and then you can do the curve fitting and then get those parameters A, B, C, D etc. through the experimental condition. Now what we do? We write ln gamma 1 is equals to 1 by RT dou by dou N1 of NT G1E at constant temperature pressure N2. And now here in place of NTG what we write? This expression we write NT, and GE is nothing but this expression at constant Tp N2. Now here this x1, x2 etc. you replace by N1 by NT, N2 by NT etc. and then simplify, then you can have this kind of form. Now this one you differentiate all these terms with respect to N1 and then simplify, like in the previous case of 2 suffix Morgul equation you have done. So then you get the additional terms here. So then that if you write RT ln gamma 1, you will have some kind of form like this, some constant A1 x2 square plus B1 x2 cube plus C1 x2 power 4 plus D1 x2 power 5 and so on. So similarly RT ln gamma 2, if you do, you have this expression, that is RT ln gamma 2 is equals to A2 x1 square plus B2 x1 cube plus C2 x1 power 4 and plus D2 x1 power 5. So now here what are these A1, B1, C1, D1 and A2, B2, C2, D2? After simplification you rearrange that expression in this form, like that all the terms having x2 square terms are the factors of all x2 square terms you group together as A1. Similarly factors of all x2 cube terms you group them together as B1, like that. Then what are those A1, B1? A1 is nothing but A plus 3B plus 5C plus 7D, and then B1 is equals to minus of 4 B plus 4C plus 9D, and C1 is equals to 12 C plus 5D, and then D1 is equals to minus 32 D. Right. Similarly A2 also you have these expressions. Okay. This is A2, this is B2, this is C2, this is D2. Only that we are writing in this particular form because we know this RT ln gamma I is having sigma, is having some factor, like some constant, and then x2 square, or let us say, because we know this RT ln gamma 1 would be having something like some constant x2 square plus some constant x2 cube, those kind of terms. Those constants are like in terms of this ABCD constants we are obtaining like this. So now if you write only 2 suffix Morgul equation, that means that B, C, D etc. are 0. So then only up to this A only there. And then you can observe this B1, C1, D1 is not having any capital A terms. Remember this capital A, capital B, capital C, capital D etc. are to be obtained through the experimental data, either from ln gamma 1 versus x2 or either from ln gamma 2 versus x1 data. That data you plot, graphically you plot and then do the curve fitting, then you get this ABCD constants. Whereas the small a1, small b1, small c1, small d1 etc. are multiplication factors of this x2 cube, this x2 square, x2 cube, x2 power 4, x2 power 5 etc. So those multiplication factors are a plus 3b plus 5c plus 7d, like that are given here. When you have only up to a term only in the generalized expression of Morgul's equation, that is 2 suffix Morgul equation, only this part only be there. That means what you get, RT ln gamma 1 is equals to AX2 square, and then RT ln gamma 2 is equals to A x1 square. It is same as what we have got in the 2 suffix Morgul's equation. Previously we have done the simplification. Now let us say if you include up to the B term, this is 2 suffix Morgul's equation. Now if you have a 3 suffix Morgul's equation, then that means you are including up to B terms. Up to B terms you are including in the generalized GE expansion form, whatever the expansion for the GE that we have written previous side. Now, the question is that how many terms should we include in the Margulis equation? Should we include only A and B, or should we include C and D also? Up to what times, what constant, what many number of parameters that you should have in GE expression? That depends system to system primarily, but that again depends on the available literature, available experimental literature. It has been found having 2 constant is more than sufficient for the majority of the system. Very rarely you need third and fourth parameters in the GE expression, right. Okay, it is not required. Even if you are having, then if in order to include those third and fourth parameters are constant, like in this case capital C, capital D, then you need to have a large number of data, and then you need to have a very reliable data in order to make a reliable curve fitting for those C and D parameters. Okay. So, based on the available experimental literature, any model that you take, if you have 2 parameters, 2 constant, that is sufficient enough to describe the model or to describe the experimental data with adequate accuracy. Right. So, number of parameters, that is A, B, C, D, etc., that are required to represent experimental data depends on molecular complexity of solution, obviously nature of the solution or the nature of component that are forming the liquid solution, and then quality of the data and a number of data points available as well. You need to have sufficiently large number of reliable data points in order to include more number of these parameters or constants A, B, C, D, etc. But however, typical VLE data reported in literature justify the requirement of no more than 2 or at most 3 parameters. 2 are sufficient enough, but at most you can have the 3 parameters, that is sufficient to justify the experimental data. This has been found by curve fitting several experimental data using the GE models with having 2 or 3 parameters. Very accurate and extensive data are needed to warrant use of 4 or more parameters in general. Okay. So, as I was mentioning, symmetric versus asymmetric activity coefficient, symmetric in the sense ln gamma 1 versus x1, whatever plot is there. So, that plot if you compare with ln gamma 2 versus x1, then both of these curves are going to be mirror images, and then one example they may be looking like this one. So, let us say binary mixture of components A and B, this is ln gamma B and then this is ln gamma A, for example. So, then you can see they are exactly mirror images of each other, and then even you can see these points are also matching exactly same, for example. And then you can see this ln gamma B versus XA curve, whatever this one is there, it is the exactly mirror image of this other curve, that is ln gamma A versus XA curve. So, ln gamma B versus XS curve and then ln gamma A versus XA versus again XA, these curves are mirror images of each other. So, then we can say such kind of activity coefficients are known as the symmetric activity coefficient. But there are kind of situations where this ln gamma B curve and then ln gamma A curve, when they are plotted against XA, then they are entirely different from each other, they are not mirror images of each other. So, then those activity coefficients are known as the asymmetric activity coefficients. So, for example, these plots are shown here. So, this ln gamma B you can see here, it is very different compared to ln gamma A versus XA plot, they are not mirror images of each other. So, these things are known as the asymmetric activity coefficients. So, the references for this lecture are given here: Engineering and Chemical Thermodynamics by Koretsky, molecular thermodynamics of fluid phase equilibria by Prosnich et al. And then chemical, biochemical and engineering thermodynamics by Sandler, and introduction to chemical engineering thermodynamics by Smith et al. Majority of the notes that has been presented in this lecture are taken from this Prosnich et al. And then couple of figures are taken from this reference book Koretsky. Thank you.